Hi guys, so tonight we're going to be talking about enzymes. Enzyme proteins, meaning that they are made up of amino acids and are produced by the cell. They act as biological catalysts. So in other words, they just speed up a rate of a reaction. They're not going to make a reaction happen that would not already happen, but they make that reaction go a lot faster. Enzymes are highly specific, both in the reaction and the substrate that they bind to. So in this example, you can see that on the left, you have a substrate, or also known as a reactant, and then you have an enzyme that works on that substrate or reactant to produce a product. So a little bit more, a term that you can see, the substrate for this example is cornstarch. So you can see at the bottom, starch is a long molecule, very, very long. You can see the ellipses there that say that the molecule keeps on going. And if you use an enzyme called alpha amylase, again, remember, those are made by the cell to do a job. That alpha amylase comes in, cuts that starch into smaller molecules called dextrin. So those molecules, those smaller molecules of dextrin, would have been made, but it would have taken a really long time. So it would happen when the starch starts to degrade and become a lot smaller. So since an enzyme is a protein, we know that it's folded up into a three-dimensional shape. Here in this picture, you only see a two-dimensional shape. But what's super special about an enzyme is that it has an active site. So you can see here that the enzyme is represented as the dark blue semicircle with the square and the triangle. That is an active site. That active site is like a dock where reactants or substrates can temporarily bind or anchor themselves. The enzyme can work on that substrate and cause that reaction to happen. So for this instance, the substrate is the yellow semicircle. It binds to the enzyme, and then after the enzyme has worked on it, we now have two pieces. Enzymes can put together substrates, or they can also take them apart. You can see the enzyme hasn't changed shape after it did its reaction, and it's ready to find another substrate to break apart. So the lock and key is a specific theory that says that a substrate has to fit into the active site of an enzyme, or else the substrate won't work and the enzyme won't catalyze the reaction. So it makes a lot of sense. So if you think about a lock, a key fitting into a given lock, you've got all these grooves and the key has to fit precisely. That theory has been modified a little bit recently by some scientists who now believe that there's this induced fit theory, so that the enzyme must still fit like a lock and key, but you have to change the conformation a little bit of that enzyme so that it hugs the substrate a little bit more, make it fit. So enzymes are pretty amazing in the way that they can catalyze a reaction over and over again and continue to be the same, stay the same, never change. But eventually an enzyme wears out. So there are certain conditions that will stop an enzyme from working or even working as well. Remember, enzymes are three-dimensional structures. They're protein folded up into a certain conformation that has an active site. And the enzyme's ability to function depends on this three-dimensional shape, where that active site is. The bonds that are forming within the atoms between the amino acids that give the enzyme its shape are very, very important. And things like pH, temperature, or the amount of salt can disrupt these bonds, or called denature. You can see the picture. We have an enzyme that's all folded, and you have an active site. But after it undergoes denaturation, the enzyme has unfolded, so those bonds that were holding it in that shape have now have gone away, and the enzyme is flat. There's no longer any active site, so it's altering the enzyme's ability to function. So the things that can cause enzymes to denature or to stop working are low temperatures. So molecules are going to move slower at low temperatures, so enzymes are going to work slower. Their job is to enhance and increase the rate of a reaction, but you're going to be able to, the rate is going to be slower just because molecules are moving slower. High temperature. So molecules move faster as the heat, but at some point when the temperature gets super high, the enzymes are actually going to break those bonds that hold it into its shape, and they're going to denature. That active site is disrupted. And then low or high pH, they can act like a high temperature by disrupting these bonds that make the enzyme into its three-dimensional shape, disrupting them permanently. So every enzyme has an optimal pH. It's not neutral. Some enzymes work better in acidic conditions, some work better in basic conditions, and some work better in a more neutral condition. But we want to make sure that when you have an enzyme, you'll be able to see that we have to have them at the right temperature, the right pH, and also the right salinity. And finally, enzymes are named a certain way. So you will probably see a lot of enzymes that are named with ACE. So A-S-E, the ending ACE. And so what they do is scientists, when they're naming an enzyme, take the substrate that an enzyme is going to work on, replace the ending with the word ACE. So proteins that would work on cellulose, those would be cellulase, those enzymes that we call cellulase. Or proteins that are going to be working on amylose, or starch. Amylose is another name for starch. Those would be amylase. So the example I showed you earlier was alpha amylase working on starch to break it down into dextrin. So there's a couple of other exceptions to the rule, like trin and pepsin. But when you see the word ACE, you know that that is an enzyme. All right, hope you guys like enzymes. We're going to be doing a great activity tomorrow with paper race and then doing an activity on bioethanol.